Great. I've broken my curse. So I will hand this over now to our first presenter. Presenters, I didn't, and apologies again. This is my first time doing this, and I made the mistake of not communicating um, the time expectations. If you could try to stay within 15 minutes or right, give or take, that'll allow us some time for questions at the end. So I will hand things off now to Adrian. Adrian, you should be able to share your screen. I've made you a co-host, so feel free to take it away.
Oh, thank you very much, and really appreciate this opportunity there, and really appreciate the work that you're doing, and you're doing the recording very well, so no problem with that. Anyway, so my name is Adrian. I have like a mixed background, engineering, computers, and lately, and this is more like my hobbies, like molecular biology, with everything that it entails. And as part of this molecular biology space, I have to, well, I couldn't afford lots of things that I needed to do that kind of experiments and everything else. So I had to kind of go into building a lot of the equipment that I was using. So this project that I'm going to show you started kind of an odd way. I had this from some of my friends in here from a company in here. I have this box, okay? And in this box, there's a little bit, some holes in here. And in those holes, see, you can put these tubes, okay? And I'm sure you can see them, and there's some liquid in there, not a huge quantity, 100 nanoliters in each one of them. And this is a box that one of the local companies in here built during COVID. They were not in that space, they are in the laser space, but they built this one because with this box, it's one of the simplest boxes that you can read if a DNA contains a certain DNA string or not, okay? And it's called LAMP. That's the acronym for it. You probably heard of PCR, which is the standard way to see if somebody has that virus or not. But this is a general box. So basically, if you look at the DNA as a string of letters, it's going to tell you, oh, do I have this substring of letters in there or not? Okay, so do I have Jamaica string of letter in Son of Jamaica Boney M song or not? And if it is, yes, it's that organism, and if it's not, it's not. Anyway, so I was trying doing this stuff with the box, and it wasn't working. Okay, and one of the things that I was suspecting was that the so-called primers, which are these smaller strings, were not calculated properly. Now, I took all this stuff to make it simple. I took it from a paper that was published by somebody, and it didn't work. Okay, so I was trying to figure out, well, are these correct or not? And there are lots of places on the internet where you can calculate new primers, but there was none of them where you could check some primers that already existed. And the procedure is fairly complex. So it's like two strings that kind of stay one on top of the other, and then they open, and then these smaller strings come and attach in some places, and then something else comes and makes these smaller strings longer. And then at one point, they kind of have to curl their edges, and it was very hard to do it. So I was trying to do it, like, can I do it on paper? It didn't work on paper, okay? And then now, if you are in molecular biology, many times you have to work with these long strings. You have to look at it. The strings of DNA or amino acids or anything else. And everybody is using 2 or 3 programs to do that because you cannot do it on paper, okay? So now let me see if I can share this. Which one is the biggest, the easiest way to do it? Probably this, okay? And okay. Yes. So you can see my screen, my share screen. Yeah, okay. So I decided, okay, let me see if I can use one of these programs there. And I looked at them. One of them is called Benchling, one of them is called SnapGene, and the third one is called Genius. The Genius one is the most expensive one. The SnapGene is fairly expensive. The Benchling is less expensive. But look at the prices. the benchling is 354. No, sorry, this is not even correct. The order is not correct in here. Actually, the benchling is about $20,000 per year for 5 users. The SnapGene for academic user is $350 per year, and the Genius one is the most expensive one of them, and I couldn't even find the prices for that. So what does it show you? These software, these pieces of software are quite expensive, okay? And strangely enough, there is no open source software for that. So I thought, okay, maybe I can start something like that. So maybe, of course, it takes a long time to develop something like that, but maybe I can just develop this as a seed for open source DNA and amino sequence manipulation tool there. Okay. And yeah, so this is how I started. And I started, well, of course, I called it something. And I wanted to do like an open source application to manipulate DNA, amino acid sequences. And I wanted to fill out the gap in available tools there. And I wanted to do something a little bit more than that. I wanted to make sure that it's extensible. You can customize it by yourself. Now, Genius is quite extensible. However, it's very expensive and also doesn't give you access to the full code. SnapGene, I don't know if it's extensible or not. Probably it is. Benchling is not at all. So that was a big problem because in molecular biology you have all these algorithms that come left and right, and you want to be able to add something, to do something for yourself, to do something for your project. So, but you cannot do it like that. So again, because I couldn't figure out the primers by hand and by writing it on a piece of paper, I decided I'm going to go with this one. And guess what? I found out, and actually I knew from before that in Scotland there's this group that developed some software, and they created a powerful library. It's in Python. It's called BioPython that has a lot of the algorithms that you need. Okay, but there was no interface for that. Okay. And of course, in my case, I was looking for this LAMP reaction, which is a fairly complicated one. But the PCR reaction, which is like the previous one, it's the same as it's kind of almost like a subset. Okay, and there were some other features that at one point I needed, and it was like this virtual gels there. Okay, and okay, and that's pretty much it for this part, and I'm going to go in the software right now. So of course it's at GitHub. It's fully documented in there. If you are at GitHub, you can look. I have lots of other projects in the molecular biology, or you see on the right side there, but there are much more than that. Now let me see if I can switch, and if I can move to the software. Can you see it? No, you cannot see it. Okay. So how do I do this? Okay, share. How about now?
We can see it now.
Oh, okay, perfect. Perfect. Let me move this. We can. Okay. So the software, the window is fairly simple. You have to open a file. In this case, when I was doing this LAMP assay, of course, I didn't want to try with virus or some pathogen there. So I decided to go with a simple solution in which I'm going to identify if a meat contains pork or not. Why is that? If you go to the grocery store, pork is much cheaper than beef, and some people in ground beef, they will include some pork. So that's a test that some of the countries do perform from time to time. So this would be the sequence, which is exactly what I was telling you about, right? You can see this long string of letters, and you know, obviously it's very long, and it does have some labels on it. Okay, and you can. It's always two. Well, in this case, it's two strands: the top strand and the bottom strand. And of course, you can see the letters. Each one is it's a DNA molecule. So adenine, thymine, guanine, etc. And normal software will not give it to you so colorful. We can change this so it's not colorful. So normal software will give it to you something like this. And so there's lots of preferences in here, as you can see. So the other good thing I was thinking about for the students, I was thinking, okay, you know, if you write redrum somewhere, you were gonna read it as redrum because you read from left to right, especially in Latin-based languages there. But you can read murder if you go from the right to left, exactly, like in Hebrew or Arabic. So these strands, these strings in molecular biology are also oriented. And students always make the mistake that do not understand that, so they read it from the wrong side there. So one of the feature I put, if you can see there, I inverted the letter, so it's clearly that this one, it goes into the other direction. It's not gonna, this is not the beginning of this string. The beginning is somewhere far away to the right there. Okay. And the other thing is like these molecules kind of attract each other. Think about like a magnet, like a north and south. So A would be north, T would be south. So they attract each other. But in molecular biology, you have two. Imagine that you also have like east and west that will attract each other, but not attract with south and north. So in this case, it would be the other two, the C and the G. And the force of attraction, if you look at this little, actually, I can probably make it bigger. Yeah. If you look at this, the links in here, they're actually GOC is a powerful attraction because it has 3 links between them, while the TNA is two ones. So these are kind of some features that I added just for people that are newer to this field. But the actual important part is, and I'm gonna make it small again, is the fact that you can do a little bit of simulations. So let's say that again, I'm going to load the same. So same DNA. So this one and here. Okay. And you see that these strands are already connected between them. There's an operation called denaturating, which means that we practically disconnect these strings. So you can see like that. And then you can add these shorter strings, which are called primers. So in this case, let's say I'm going to add B3 in this case. And you see in here that there's some other letters. These letters will actually, in the liquid, will go and it will try to kind of bind, to cling to the complementary letters. So one of the things that you have to try to understand is like, do these other strings have the complementary letters of this one? Because in that case, they will bind it. If not, they are not going to bind it. So it's almost like a string finding kind of features. So this is called annealing, this binding thing. And let's see if it does binding. Well, in this case, it seems to be binding in many places, and it's going to go to the first one. And now look at it. It went in here. Okay, C with G, G and C, A with T, etc., etc. You cannot do this by hand. I mean, you can do it by hand, but it would be very, very painful to do it. Okay, and the other operation would be elongation. So there's a certain molecular machine that will actually start adding more letters to in continuation of this. When I'm saying continuation, I tell you that you read it from right to left in here. So it will put the next letter, next letter, next letter. So the next one would be a G because C goes with G, and then A because it's complementary to T, and then another A, and so on. So if I say elongate, you see it did find all exactly, it did exactly what that molecular biology engine will do. And yeah, so this is another feature that it does. And it's very common, and it's simulating it properly. Let's say another one, which was the other one that was coming from the other direction. So this one normally would cling to the lower strand there. So I yield somewhere in here. Yeah, you can see it in here. And then we can also do elongation on this one. And again, we did the elongation. Now, I added another feature, which was kind of a strange thing. Usually the sequences can be very long, can be like, 20,000 letters and so on. That would not be unheard of. Sometimes they can be into millions. And most of the time you are interested only in specific portions in here. So there's a specific portion and another specific portion that's interesting in here, but then there's nothing, well, another one in here. But then there's a long portion where you cannot see, you're not very interesting. And then at the end, sometimes you get some more. So I added another feature called shrink, in which I basically shrink the unimportant portions to just some gray letters. I take only 2 or 3. And now you can see in one screen very easily all the parts that are important to you. And this feature doesn't exist in the other 3 software that I was telling you about. So, and let me show you the of course, this one at this point, it has some kind of debugging features there where it creates it has some pre-tests, like tests that are already so yeah, the idea is like you can build on a number of these operations, denaturate and yield elongate. You can put them in a certain sequence, and you can add them as a macro. And then in this case, something like this would be the macro. Okay, and this is probably the most complicated one. This one, yes. Okay, so in this case, I'm not sure if you can see, but actually this strand, which used to be horizontal, so longer, the string was like this, it actually bent on itself because it just happened that the end of it contains letters complementary to something else that was on the string before. This is called a hairpin. You see, so T glued with G, C. Well, actually, this is not glued, but these ones are. So these 4 A's are glued with the 4 T's. And this is called a hairpin, and this will stop the machinery from going and doing the. It blocks it. So, this can, if that happens inside your body, it can be, a disease or something like that. But this lamp, it actually uses this feature of bending the DNA on itself, which is again very hard to see. So how are we doing with time there?
We are. I actually just unmuted myself to give you a time check. We're about at 15 minutes right now.
Okay. So this is kind of what it is, but the main idea that's in here is that the other 3 pieces of software that I was telling you about are actually the companies actually don't invent all the parts of them. They actually take them from usually papers that coming from the environment, from the academic environment. 3 pieces of software that come from there, and they aggregate them. So my idea was, if I start something like this and somebody's going to add more and somebody's going to add more, because it's very easy, it's extensible, it's written in Python and it's open source, maybe we can get one tool like this that is going to be able to replace the expensive ones and actually maybe even do better in some respects in terms of being able to be much easier to extend it. And that's one of my projects. And again, my projects are usually based on, I need to do something and I cannot do that, or it's too cumbersome. Let's find a solution, but then let's take that solution and let's make it available to other people that might do the same thing. So I have to write it a little bit nicer and of course publish it on GitHub and everything else. So I think I thank you very much for your attention, and yeah, if you have any questions, let me know.
Thank you, Adrian. That was fascinating. It seems like an enormous amount of work, and I'm sure that there are lots of questions and a lot of interest in this. I wonder if we might, I don't know how this has been done in the past, but I wonder if we might withhold questions and do group questions at the end. That way we can ensure that Joe has plenty of time for the next presentation, and then we can just open it up for a group discussion in the remaining 10 minutes. So Joe, if you wanted to go ahead and take it away, I maybe also aim for 15 minutes and I'll provide another time check as needed. Joe, it looks like you're muted.
So I'm not used to Zoom. We're very much a Teams shop. Can you see my screen share okay?
All fine.
So there's a browser window. It says better hardware, better research. Hi and thank you all very much for welcoming me to your community call. I'm very new to all this. So my background is in software. I'm a research software engineer for the UK Centre of Ecology and Hydrology. I've recently taken up a small fellowship with the Software Sustainability Institute in the UK, and I want to talk a bit about what it does and why a software foundation is supporting open source hardware, and hopefully find out how I can help Gosh, and maybe how Gosh can help me. So that's me in the green t-shirts on the right. Obviously, I haven't changed a bit in 20 years. Although quite a lot of the infrastructure has changed in this time. This image is from the first OpenStreetMap mapping party. So I was a very active contributor right at the start of that project. And I got involved in it through community wireless networks, back in the days before there was widespread home broadband or mobile devices. Idealistic groups of artists and hackers were building things like Consume.net, Wireless London, and we needed a base map and started our London free map to support that and then folded that into OSM. And involvement with that project, it definitely changed the course of my professional life. And I've spent maybe the last decade or so working on research software of different kinds for several different organizations that all do land surveys. And most recently, that's at the UK Centre for Ecology and Hydrology. We have a small office here in Edinburgh, several scattered around the UK. I've been there for just over a year, and I'm part of a small team of RSEs, research software engineers, whose job specifically is to work with lots of different science areas and help harden their code, make it more reusable and openly reproducible. CH has a very long history. This picture is of Lake Windermere, where there's been continuous environmental monitoring, lake sampling for 130 years. And the organization has a huge remit. It takes in pollution, atmospheric chemistry, air and water quality, lots of biodiversity work. So it's field samples, it's labs, and a lot of field sensors and electronic monitoring. It has a really interesting sort of in-house engineering workshop. It's like an in-house hackerspace that through my eyes is being underexploited as a group of people. This is some of their work from a recent paper. I love it because it's not electronic at all. It's a river flume, and I spoke to them about the challenge they'd had in sort of making effectively a buoy that would neither fully sink nor fully float, while it collects algae cultures in ceramic plates, which then get replaced, and observe properties of the river chemistry. They also do teaching for third parties. So this was a field electronics and sensors course, which took you from, zero knowledge, absolute basics, to building a solar powered outdoor sensor installation in 2 days. It was an amazing experience. Um, and that lots of different research groups in the organization are doing either working with open source hardware or doing open source adjacent projects using components, bits of infrastructure. But it's all kind of scattered around individual groups. And for the large infrastructure projects, the national capability work that it does, the organization is buying in proprietary devices, data loggers. That's a previous colleague of mine who's now sadly left the organization, Alba Gomez Segura, setting up an AMI system, which is a kind of in-house equivalent of the moth box, like shines a bright light, attracts moths, takes repetitive images of them, which that group is also building some of the bioacoustics capabilities of the audio moth into now. So when I started at the organization, I saw this range of work and I thought, why isn't open source hardware being treated in the same way as open source software, as something that's intrinsic for the development of high quality open science? There's an organization in the UK called the Software Sustainability Institute, the SSI. They've been going for many years trying to build culture, to lobby organizations, to help people develop their own training around open source and its critical role in research. They have a fellowship scheme, which and their fellowship scheme supports you for a year. It gives you a small budget that's intended mostly to be spent on workshops, community organizing, in support of their mission to help people build better software and more sustainable software to enable world-class research. And I managed to interest them happily in taking on some open source hardware remits with a proposal to try and organize and facilitate a series of workshops that bring together field researchers with hobbyist electronics folks, particularly across the UK's network of hackerspaces that I've had a long connection to. This is a very representative image, rainbow cat ears and all, of our local hackerspace in Edinburgh, where the open source hardware summit is coming this year. So I've reserved the space and I've got the budget for the day, and I was hoping to run the first of this series of workshops right before the OSH summit. But now I'm having a bit of a crisis of confidence about it, or I haven't been able to reach the field researchers in the same way with the same understanding of language as I have the hackerspace folks. And some of the issues there are to do with, they're very similar to the issues we encounter as software practitioners. Most researchers just want data, they want outcomes, analysis. The implementation details of the instruments aren't necessarily particularly interesting to them. I've also been advised to try and focus on specific concrete use cases, but I'm quite reluctant to do that, to kind of go into that setting with preconceived judgment about what I'd like to come out of it. This image is from a presentation by Libby Miller. I'll drop a load of links in at the end. Libby was part of the BBC R&D department. And this is it's a design fiction of a mushroom sensor from the year 2035 that was designed in workshops with kids 8 to 9 years old, facilitated by folks from their R&D department. It's a lovely project, and it reinforces for me the value of a process of social invention or social prototyping. And I guess the other reason that I'm trying to do this is it's pure self-interest, because a lot of the current interest, certainly amongst my colleagues, in open science hardware for environmental sensing it's driven by AI applications, by automating manual tasks, or by doing novel kinds of analysis, bringing lots of different data sources together. And it's very, very vision oriented at the moment. And now my previous role, I was in a deep learning and computer vision team. We did GeoAI. And while we were in applied research, we had a lot of creative freedom and our work was quite abstract, but it was in quite close harmony with defense, security, financial applications, which professionally I would like to avoid. So when I found myself being routed towards imagery analytics projects, when I joined UKCEH, that partly motivated me to want to explore open hardware, sensor types, different ways of solving the same kind of problems or seeing the same kind of things in ways that are computationally cheaper, uh, lower power, and much less intrusive, and not end up going through yet another professional iteration of accidentally building more surveillance infrastructure. I show this image. It's from a theoretically, in principle, a lovely project by a colleague called Jenna Louise Lawson. It's got the micromoth, like the micro sensor from AudioMoth, mounted into a drone, which it's firing sharp projectiles at different layers of the tree canopy so that they can do bioacoustic analysis on birdsong patterns at different levels of the tree canopy. And with the best will in the world, a lot of the larger scale applications um, of AI and environmental science now just look like more surveillance infrastructure, but being turned on the biological world. And I've always suffered from a tendency to be able to sort of preview a bit too immediately the negative applications of technological work. It's not a terrible tendency. And in environmental instrumentation, there there are so many. And I certainly, I want to do social invention because left to myself, I come up with terrible ideas. Um, this is this is one of them. It's the Larawan Gateway dog backpack. Obviously, the dog is out for a walk anyway, and it's picking up all the sensor information from the fields. And then when it stops to pee against this tree, then perhaps there's an aggregator there built into the there's a whole range of inventions to do with animal instrumentation, which I've heard were some of the kind of the original conceptual origins of the micromoth, that I'm not sure that we need to exist. Um, Another inspiration for me recently has been the work of Dan McQuillan, who a few years ago now published a book called Resisting AI, and his more recent lectures have been about decomputing, about how we can manage to make technology that has got some kind of built-in resistance to large infrastructures, that have that tendency to be repurposed towards social behavioral control. And a recent phrase of Dan's I liked was resisting scale as a heuristic for the way forwards. So, I want to try and end on an up note, and show this. This is a project. It's the Mini 2 Picasso. It's a project by an open hardware designer here in the UK called RC 2014, which it began life as a sort of very extended April Fool's joke, but it's a shippable product. I'm about halfway through building mine. I sold it very slowly. Every kit is unique. The design is intentionally wild, but there's so much kind of joy and care around a little project like this tiny retro computer. And that's a that that's something I'd love to see more of in the world. I see open source hardware as absolutely essential to that, as much as I also see it as a conceptually essential part of digital research infrastructure that supports open and collaborative science. I've bitten off a big aspirational piece with my workshop plan, and any comments, feedback, recommendations, pointers to prior art from the Gosh community, I'd be so grateful to receive. There are many, many more links on this last page, but I'll paste it into the chats. Thank you.
Joe, thank you. That was fascinating. And I appreciate that, the heartfelt delivery, the very genuine delivery. Thank you so much. I'd love to open the floor now to questions for one or both of our presenters, to the audience. Apologies. Feel free to just raise your hand or come off mute, and we can get this conversation started.